My presentation is about artificial intelligence-based affective computing to facilitate human-robot interactions. During the presentation, I will give a brief introduction of robotic and human-robot interactions, that we will see what is affective computing and how it is used for human-robot interaction, and then the artificial intelligence technique that are used in this field. And we will focus on the visual domain analysis to compute affective computing and with the goal of facilitating human-robot interaction. And then, other than the visual domain, we will also see how this can be applied in physiological signals analysis. So, what is human-robot interaction? Just a brief background. We see the robot started to be in our idea until 1920, and they were the main characters of science fiction. Indeed, robotics, mainly service robots, has long been the subject of science fiction. So they were born more in our idea, in our thought, before being actually in our society. Indeed, the first robot was a robot in a company or industrial field. And then they started to go out from company and be part of our society. And we have the aerospace robots, for example, social robots, or assistive robots, and also humanoid robots. So a lot of application for robotics. All these robots have the same cycle of components. So they are based on these three components: sense. So they have some sensors to sense the environment around them. And then the computer will allow them to take the information from the sensors and establish which action to perform. And then they have actuator to perform the action. So all these robotic applications have the same cycle: sense, think, and act. In this, in the robotic, we have also affective computing, which is a field for human-robot interaction. In the human-robot interaction, the affective computing can be considered in three main areas. So the goal of this affective computing in the human-robot interaction field, one is the goal of developing systems that can detect emotion, or developing systems that can express emotion, or systems that feel emotion. We will focus on the development of systems that can detect emotions. And so how can we detect emotion? How can a system detect emotion? Then where the affective computing is born. So affective computing is indeed the study and development of systems and devices that can recognize, interpret, process, and stimulate human affect or human emotion. And this is currently one of the most active research topics in the human-robot interaction field. Furthermore, it is having increasing intensive attention. And it also encompasses disciplines such as engineering, education, sociology, psychology, cognitive science, and others. So the main question behind that is, so why do we want computer to emphasize that? To recognize our emotion and be responsible to be responsive to our emotion. Why do we want that? For different reasons. So a computer can play a role of emotional mediator, for example, making other people aware of someone's emotion when the social help in overcoming the emotions is needed. One example, but also special application, for example, could adjust decisions to the user's emotions, or a computer itself can play a role of the user friends for pseudo-social psychological help. So in conclusion, a machine with affective computing capabilities will be a powerful assistant for improving and support our emotional well-being. How can we perform affective computing? There are two methods of emotion recognition. The first is based mostly on facial expression, gestures, or speech analysis. So all the things that we can see and can perceive with our eyes. So we can see the facial expression of our interlocutors, or the gestures, or the speech analysis. And this is one of the channels that can be performed the affective computing. The other channel is more based on what we cannot see, so the physiological signals. So it's more related to some unconscious signals, such as, for example, our heart rate, or breathing frequencies, or our, for example, thermal variation. And we will focus on both of these aspects. And both of these channels have some good aspects and worst. For example, in the first channel, so the most used way to perform affective computing is using facial expression analysis. That's becoming very popular way to perform affective computing. There is the good things is that there is a lot of data that we can use to perform facial expression recognition, but the worst way is that there is a problem called social masking, that we can maybe falsify our facial expression. So the facial expression did not really correspond to our emotions. On the other side, physiological signals, we don't have this problem. So we cannot control our physiological signals. So of course, we cannot classify emotion if someone is analyzing our physiological signals. But the worst part of this is that they are mostly used contact sensors. So normally this physiological signals analysis is performed by using this sensor, which are in contact with the person's skin, and it can be a source of distress. So it can in some way be a noise for our emotion recognition. So both have the good aspect and worst aspect. Now, how can we apply artificial intelligence in affective computing? So we know that artificial intelligence algorithm can be divided also in some subcategories, which are machine learning, or also neural network and deep learning. We will see both machine learning and deep learning. We have here an example of a deep learning architecture. And so we will see how this can be applied in affective computing. The first channel, so with a facial expression, we use artificial intelligence, and more specifically, deep learning approach to recognize facial expression, or to recognize the affect of the person. In this way, there are two ways of recognizing the emotion in here. The psychologists developed some models. For example, we have a circumplex model of affect, which is formed of arousal and valence of the emotion. So we can divide the emotion with the valence and the arousal. Or we can classify emotion based on the definition that Ekman gives of the 6 basic emotions. So this categorization of the 6 basic emotion is related to emotion such as happiness, surprise, anger, disgust, sadness, and fear. So these are the 6 basic emotion, and we wanted to classify this emotion by looking at the facial expression of a person. How we can do it? We can, what we did, we used the artificial intelligence algorithm, and specifically in here, we used convolutional neural network. And this was the architecture of our neural network. So the input of the network was a picture of a face of the subject. And then the output of the neural network was these 6 classes. So the network would say to us if the subject was happy, sad, or one of the 6 basic emotions that we wanted to recognize. So this was the architecture, and so we can see that the network was composed of for a convolutional layer, and the output of the first layer, which is the one that we can study, is more easy for us to recognize which are the output of this first layer. So in here I reported the output, and so we can see the silent feature where the network focused to give us the output. I reported only on the first convolutional layer, not to the others, because this is the most easily to understand. So then the output was the 6 classes, and this is nice because we have a lot of data in also in the web. So what we used was a public data set, and the network output was giving us this accuracy, and for each of the 6 emotions we detected an accuracy. The accuracy, the expression with higher accuracy was the happy and sad, where we reached 19.1 and 90% accuracy. Other expressions, such as, for example, angry or fear, they give less accuracy because this system, the model that we developed with our convolutional neural network, this model was mostly confusing angry with the fear emotion. So in that emotion, they were not a higher accuracy. The overall accuracy reached was 70%, which is not bad, considering that we have 6 classes. So now, how we can use all these algorithms for helping or for facilitating human-robot interactions. So the same model that we developed, we used also in a robotic platform. As a robotic platform, we use the Now Robot. Now Robot has different sensors, and it is very nice because it's very open source. So we have this SDK that can be used to program it and also to receive input from sensors. So we use the Now webcam that he has in his forehead, and we took the image and we applied to the image our model that we developed. And so we were able to have the output and say which was the expression of the interlocutor of the Now robot. So in a certain way, we give the robot the capability to recognize the facial expression of the interlocutor. And this was the results. So during the interaction, the robot is not really clear here, but the robot, we say he could recognize the expression, and here is the output of what the Now robot was seeing. So the final goal is, how I already said, it was to facilitate this interaction, because it is important from the robot to have an idea of what the person is feeling, to also to decide what could be the next action to perform. And so in this, now what we did, we applied artificial intelligence for affective computing in the visual domain. But what about the physiological domain? So in the physiological domain, we mainly focus on thermal imaging. Why? Because we wanted to overcome the limits that I told you before. So the fact that the contact sensors can be a bias in our emotion recognition, because having a sensor in contact, so make the person most stressful, could make the person more stressful. So it can be a noise for our emotion detection task. So we use thermal imaging. Thermal imaging is a contactless technique that allows non-invasive measurement of the human body physiological response, and mostly on the autonomic nervous system functioning. And specifically, some of the physiological effects that are produced by our autonomic nervous system. And some these responses are more the related to the pseudomotor response, for example, or the breathing rhythm or the heart rate. All these parameters we can monitor with our thermal infrared imaging. And so how can we use then the machine learning or artificial intelligence algorithm in affective computing by analyzing physiological signals? How can we do that? We can do it, and I show you how in two projects. One project is the robot avatar thermal enhanced learning tool prototype, and the other is the sensing robot. So what is the robot avatar thermal enhanced learning tool prototype? So this prototype is aimed to be a learning tool. It is composed from a robot and the avatar. So you can see here, we have a robot and the avatar. So the final goal of this prototype was designed for infants who are deaf and may not receive sufficient language exposure. And for them, the avatar was performing a nursery rhyme in the American Sign Language. And the avatar was exposing the baby to the language, while the robot was able to capture the infant attention. And when the robot captured the attention, it turned its head to the avatar, and the avatar started to produce the nursery rhyme in American Sign Language. In this way, this prototype can increase the infant attention, because the robot would be able to understand the real moment where the baby was ready to learn. Okay. So we say the moment that the baby was most engaged with the system. And how do we recognize that? We recognize using physiological signals, and in this part we use thermal imaging. So by analyzing the thermal variation of the nose-tip of the infants during the interaction, we were able to distinguish three levels of the subject engagement, the infant engagement. And we were able to perform this by using machine learning algorithms that can give us the classification of these three states of engagement. The second project was the sensing robot, and the sensing robot was used to facilitate the child-robot interaction. So in here, the interlocutor of the robot was the child, but not infant. The subjects were from 4 to 5 years old. And the robot was interacting with the child, and it could perform two types of action, and it could perform one or the other based on the child's state of engagement. So the robot was composed of a video camera and a thermal camera. And then the camera was connected to a model that we developed, and we call the computational psychophysiological module, that give us the outcome. There was a three class of engagement, so positive, neutral, or negative engagement. Based on these three class, the module gave the robot indication what will be the next action to perform. So in here we see two examples of the interaction between the robot and the child, and we will see that the robot was telling a fairy tale. so just telling some fairy tale. And at the end of the fairy tale, he asked the subject if he seems bored, and the robot, the child didn't respond to the robot, let's say, so the robot recognized the baby was bored and asked him, "You seems bored, don't you?" He didn't respond, but it seems really bored. So in that way, the robot at the end will be able to decide, okay, so now I'll change the action to perform. In the second experiment, we see the robot singing a song to a child. And so we can see here the outcome of our module and see that the outcome was a level 1, so it detected a positive engagement. In the baby was actually having fun with the robot, and at the end the robot says, "You seems amused, don't you?" And it actually seems amused, so it keep on singing a song. How would you perform the outcome? So this 3 level. We use a machine learning approach, even if it was not a deep learning, it was just only one hidden layer because we didn't have that much data. So we need to collect more data to perform more complicated algorithms. And the accuracy in here was also 71%, but this stage the class were only 3 classes, so positive, neutral, and negative. And we do perform this only based on the physiological signals, only based on the thermal signals of the baby. So in conclusion, artificial intelligence-based affective computing, together with thermal infrared imaging and facial and motion recognition analysis, so both together can provide psychophysiological insights that help investigate robot influence on children cognition, learning, interaction, social, and moral development while playing with the robot. So also, the current research provide compelling evidence of how the use of artificial intelligence approach combined with thermal infrared imaging can be a powerful tool to support and to facilitate a spontaneous human-robot interaction. The future purpose is also to acquire larger data set, mostly this related to the physiological signals data, and in the perspective of employing advanced deep learning algorithms. So the integrate of the artificial intelligence, thermal infrared imaging with other also physiological signals, such, for example, wearable technologies. This will help us to have more data and also to use the advanced deep learning algorithms. However, anyway, artificial intelligence-based affective computing, so we combined with the facial expression and physiological signals with the thermal infrared imaging has the potential to render revolutionary advance across multiple applications. So thank you for your attention, and if you have any question, I will be glad to answer. Or here also there is my email if you want